Hi everyone, and welcome to this talk. My name is Behrouz, and I'm going to introduce our recent work optimizing machine learning workloads in collaborative environments. Data science and machine learning are interdisciplinary fields, requiring knowledge from mathematics and statistics, computer science, and domain knowledge. And on top of that, there are tens, if not hundreds of different tools and software products enabling rich model training and data processing available to data scientists. Learning all of these by one user is very difficult and it's not impossible. Therefore, to have high quality data science applications, we need to have effective collaboration among users. To that end, there has been several breakthroughs in recent years. For example, Jupyter notebooks have enabled sharing of code and results. Containerized environment have enabled execution and deployment of these notebooks on the cloud, and platforms such as Google Colabratory and Kaggle have enabled effective collaboration among users by building infrastructure around these tools. However, there is still one big problem, and that is lack of data management around these generated data artifacts. These scripts and notebooks typically have tens or hundreds of intermediate data artifacts, and if one user would like to access one of these, they have to re-execute the entire notebook in order to recreate the result they're looking for. We look into a Kaggle competition, and the top 3 notebooks of that competition, they generate around 100 gigabytes of data artifacts, and they were copied 10,000 times. What this means is that this lack of data management could lead to thousands of hours of redundant data processing and model training, which we would like to avoid. And that's where we come in. We propose an optimizer that can be integrated into the existing collaborative platforms, where on the client side, which could be inside these containers, we parse user workloads into a DAG, a directed acyclic graph. And on the server side, we optimize these workloads through materialization and reuse. And once they're executed, we annotate them with some extra information which we can use for future optimization. Our concrete contributions are the following. We have an experiment graph, which is the collection of all of the workload DAGs that have been executed. We have a materializer component that decides what artifacts to store. And we have an optimizer which offers a reuse algorithm to find the optimal execution plan of user workloads. Now, the materialization problem, as I said earlier, the size of the intermediate data is very large and we cannot store everything. Therefore, given a specific storage budget, we would like to materialize a subset of the artifacts in order to minimize the execution cost. There are several challenges. For example, future workloads are not known beforehand. And even if they are, this problem has shown to be NP hard. And lastly, any solution must accommodate large graphs and fast number of incoming workloads, which is typical in collaborative environments. Our solution is an algorithm that assigns a utility value to every intermediate data artifact of a workload. This utility value has inverse relationship with the size to penalize the storage of large artifacts, and has a direct relationship in order to encourage runtime heavy, high frequency, and high potential artifacts, which are the artifacts that could lead to high quality models. Once we've assigned this utility value to all of the artifacts, the materializer component starts materializing them into the experiment graph one by one until the storage has been exhausted. While we were implementing our materialization algorithm, we realized that many of the artifacts of data science applications tend to have many duplicated columns. For example, feature selection or feature generation operations the output artifacts typically preserve many of the input artifacts. And if we store everything, this wastes a lot of storage. So in order to improve our algorithm, we added another step, which is a deduplication step, where after every time we call our materialization algorithm, we deduplicate the results, getting rid of all of the columns that appear in multiple artifacts, which frees up some space, and we can store more artifacts. We show that this improves storage utilization and runtime in our experiment. And next, now that we have our experiment graph with some materialized artifacts inside of it, when a new workload arrives, we would like to find the optimal execution plan, meaning for every artifact inside this new workload, we would like to know, should we reuse it from the experiment graph, or should we compute it locally on the container? Here also, there are several challenges. For example, the search space of the solution is very large, and an exhaustive search would have an exponential time complexity. And similar to the materialization problem, the solution must accommodate large graphs and fast number of incoming workloads. Note that in this area, the state-of-the-art solution has a polynomial time complexity, and we show that this is not suitable for a collaborative environment. Our solution is a linear time algorithm that computes the execution, the optimal execution plan with a forward and a backward pass on the workload tag. For example, here, let's assume we have a workload that has two source data sets. We have a train and train two. We perform set of operations, we merge them, and we train a machine learning model on it. The yellow artifacts are the ones that are already materialized inside the experiment graph. So the algorithm is as follows. During the forward pass, we accumulate runtimes as we traverse from the root nodes down to the leaf node. And for every vertex, we compare its load cost from the experiment graph with the accumulated runtime. If the load cost is smaller, then we load it from the experiment graph because that's the cheaper option. And if it's not, then we compute the node locally. And in the backward pass, we prune any unnecessary loaded vertices. For example, here, if all 4 yellow vertices are loaded, then these 2 vertices can be pruned from the graph because they're not part of the computation at all. We evaluated our system on a Kaggle competition, where we used 5 real scripts from the competition and generated 3 of our own. The total size of all the artifacts were around 130 gigabytes, and we compared our optimizer with Helix and a state-of-the-art machine learning frameworks, which offers materialization and reuse, and a naive system with no optimization. In this figure, we see the repeated execution of 3 of the workloads. In the first execution, the experiment graph is empty. Therefore, the runtime of all 3 approaches are more or less similar. However, in the second execution, in the second run, our approach and Helix, they materialize some artifacts into the experiment graph, and they can reuse them to reduce the time, which leads to up to an order of magnitude improvement over the naive baseline. And in this figure, we see the execution of all the Kaggle workloads, all 8 of them, one by one. Here we see that by the end of the process, we outperform Helix and naive approach by 50%. And the reason is that the materialization budget here is very small, and our materialization algorithm is able to select more beneficial artifacts for materialization, which leads to a